Your phone and your desktop PC both have CPUs, but they don't work the same way. The brain inside your phone is optimized for efficiency, while your PC is built for raw power. It all comes down to their internal blueprints, or architectures, such as von Neumann, Harvard, and newer or contemporary ones. Today we're breaking down exactly how these three designs work, why one of them suffers from fatal bottleneck, and the sneaky hybrid design behind the modern chips all around us. Let's start with the grandfather of modern computing, the von Neumann architecture. Developed in the 1940s, is the foundational design for almost every general-purpose computer you've ever used. It relies on three core rules: shared memory, data and instructions are stored together in the exact same physical RAM. A single system bus uses one set of data and address buses to move everything between the memory and the CPU. Sequential execution, it fetches and runs instructions one step at a time. Now, sharing a single highway sounds efficient, but it leads to a massive problem known as the von Neumann bottleneck. Because there's only one bus, the CPU cannot read an instruction and read or write data at the exact same time. The CPU ends up sitting idle, waiting for memory access. So how do we fix the traffic jam? We build a second highway. This is Harvard architecture. Instead of lumping everything together, Harvard physically splits memory into two completely separate blocks. One exclusively for the data, and one exclusively for instructions. Because it has dual buses, the CPU can fetch an instruction and read or write data simultaneously. No traffic jam, therefore no bottleneck. So why don't we build every CPU like this? Well, Harvard is highly specialized. It's more expensive to manufacture, complex to wire, and can waste space if one data block is full while the other has wasted space. Instead, you'll find pure Harvard architecture in embedded systems and microcontrollers. Think your microwave, your car's engine control unit, or digital signal processors. Bringing us to the modern day, nothing really fits into pure von Neumann or Harvard. It's a mix of both of them. On the outside, looking at the motherboard, is von Neumann. There's one stick of RAM holding all your open programs. But on the inside, directly on the CPU die, is Harvard. The ultra-fast level 1 cache memory is split into separate L1 data cache and L1 instruction cache. You get the cheap simplicity of the von Neumann RAM, with blazing fast speed of Harvard internally. But contemporary chips don't stop there. To push speeds even further, they use two major techniques. Instead of doing tasks one by one, modern chips do them all at once. SIMD, or single instruction multiple data. One command is sent to multiple processors to work on different data. Think of a GPU changing the brightness of millions of pixels at the exact same time. Then we have MIMD, or multiple instruction multiple data. Multiple independent cores executing completely different instructions on different data. This is your multi-core CPU running a video runner in the background while you play a game in the foreground. Finally, the CPU doesn't work alone anymore. It works with coprocessors. It delegates its tasks to them. A coprocessor is a specialized chip designed to take intensive tasks and handle them independent of the CPU. For example, a GPU which handles graphics and complex 3D math. More recently, we have NPUs, or neural processing units, for AI. So to wrap it all up, von Neumann uses one shared memory and therefore suffers from a bottleneck. But it is still great for general computers. The Harvard architecture splits memory for parallel access, so it is perfect for embedded systems or microprocessors. Modern processors take the best of both worlds, forming contemporary architectures alongside parallel cores and coprocessors.